Hey guys, what's up? Eddie Alho here with KissAnalog.com. Alright, so we're back here with the Kasun speaker crossover. It's a three-way speaker crossover. It's made for a tweeter, woofer, and a mid-range. Okay, and the crossover's 800 hertz between the woofer and the mid-range, and mid-range to tweeter I think is 4500 hertz. And it's designed for 5 to 8 ohm speakers. Okay, so what we did before in the past videos, we looked at the voltage plots on each one of those outputs. Okay, but what happens at the input? When we hook an amplifier up to this, what the heck does the amplifier see? It's not going to see all three speakers in parallel at one time, right? Because as the frequency changes, that crossover is switching in one speaker and then switching it out and switching the next one in. What's happening at those, those crossover things? And what happens, let's take a look. Let's see what the impedance looks like. Let's see what the amplifier is going to be looking at with the speakers plus all these magnetics, capacitors, and resistors hooked up. Like, what the heck? What does that amplifier have to drive? Let's find out. What we're going to do is we're going to take a calibration shot with the 4.7 ohm resistors. Then we'll take a calibration shot with the 10 ohm resistors. And then we will hook those resistors up, all 4.7 ohms resistors to each one of the three outputs, and we'll look at the input. Okay, we're going to read the voltage going in and the current going in, and we're going to take voltage divided by current to find the ohms. Alright, we're going to do that for the 10 ohm resistors and the 4.7 ohm resistors. So we'll be able to see what the impedance is with all those resistors hooked up to this guy. And then we will know what the amplifier is going to see. Alright, hey, let's do this. Okay, so just go over the circuit really quick. The input's here, mid-range output is here, the woofer output is here, and the tweeter output is right here. So all three components are here. Now, by the way, just to point out again, ferrite with the hollow quartz, cylindrical, same thing here, and these two are just air cores. Okay, 3 aluminum electrolytics, 2 polys, and some dampening resistors here. Okay, and then these are the resistors I'll use. These little 3-watt resistors. I'll use 4.7s and 10 ohms on each output. And let's see, this is the circuit, but here's the circuit broken out into 3 elements: the woofer, tweeter, and the mid-range. So all these inputs are tied together right here at the input. At the input right here. So this breaks out into these 3 filters: the woofer, tweeter, mid-range. And again, the data sheet showing the input, the 3-way crossover. This is showing it all together where I had it broken out, and the curves for each one of the things. We're going to look at the input to see what this input impedance is to the amplifier. Okay, and this is our board with our 3 outputs, and we will have these connected to, each one of them connected to a 10 ohm resistor, and then we'll put our input down here at the bottom. Okay, now here we are with the input connected. I have the current probe in line with the generator right here, and it's putting current into the positive terminal. We got the voltage probe for the positive terminal and the 2 returns from the generator and the scope right here on the return. Alright, so just for a quick scope setup, I'm going to use channel 1, channel 3, so I don't even need channel 2 in there. Current probe here, I'm using the Tektronix one, and I've got the little 50 ohm attenuator that I need for that. So let's look at channel 1 setup. It's a 10x probe, it's in 10x position, AC 1 meg, full bandwidth, and 10x. Channel 3, AC 1 meg, full bandwidth, and it's set at 10x as well. And it's set for current, so I can see current instead of voltage. But okay, so then what I do is I go to this app menu, and then on the app menu I have to go frequency response analysis, FRA. Let's go over to that, select that, and yes, I really want that, so I have to Okay, now here's the beginning waveforms. It kind of will show the waveforms up in this window, and down here it'll graph our Bode plot. As soon as I hit the run key, and gain is over here in blue and phase is over here in red. So here's a reference circuit, scope, device under test. Now of course I don't have it set up like that, channel 1 and channel 2, output and input. Normally you'd go output gain divided by input, but we're going to do volts divided by current. Generator output comes from the output of the back of the scope. There's 2 generators, but it uses generator 1. So if we go to setup, input will be channel 3, so it'll be current, and output will be channel 1. So I can select any one of those for any one of these guys. So channel 1 will be voltage, so it'll be output divided by input. So that's volts divided by current is ohms. And then 30 points will be more than sufficient, I think. We can go down to 10, but I'll just go to 30. It takes a little longer. I'll probably speed through the camera work, so you don't have to sit there and watch it. And we'll choose 50 ohm, 2.5 volts, and frequency 20 hertz to 100 kilohertz. So yeah, I think that'll work. I just have to hit the run and we can start. Let me show you the current probe. Alright, and this is the Tektronix P042. I've got it balanced out and it's set at 0.1, and I just degaussed it and I'm ready to go. So with this, this is going to the scope channel 3, and this is going to our probe. And this is the little slot where I degaussed it. Let's go watch the curves on the scope. Okay, we're ready to start the calibration sweep for 10 ohms. Okay, here we go. The voltage is the yellow one and the current's the purple waveform. So you'll be able to watch the scope kind of sweep the frequency and the auto sets and all that stuff. It's coming in right around 20 dB, it looks like. Alright, so I have it going out to 100 kilohertz, just so it's past the 20 kilohertz mark, which is right there on that gradient there. I just have it going past 100K just in case we see some strangeness happen out here. Now let's go ahead and get to the measurement menu. I'm going to change the scale over here to give us a 0. It auto scales, so let's get the a 0 here. Okay, so there's 0, this is a phase, the red, and that's 0 degrees, and it just kind of parts right around 100 hertz, maybe 200 hertz, and it drops down to about minus 15 degrees. So that's the current probe, I'm sure. It's pretty good current probe, this Tektronix. I'm using that just because it's the flattest current probe I have, and I just want to, you know, use the best current probe for right now. Let's get the cursors up. Okay, there's our cursors, and I'll move the cursor 2 out here to 20K. That's 20K right about there. And I'll move this one out here at the beginning, which is about 20 hertz is where we started. That's where the Bode plot will allow me to start. So what you can see here is the difference between them is 0.9 dB, so that's pretty darn flat. And it started at 20.7, ended at 19.71, and there's that minus 17 degrees, and it ended at 0.33 degrees. Okay, I put the 2 values in the calculator there, and one came out 9.66 at 19.7 and 10.8 at the 10.8 at the 20.7. And so the way I did that, here I'll just go ahead and I gotta erase that here. 20.7, enter, and then divide that by 20, and then take the anti-log, and that comes out to 10.839, so 10.84 I guess ohms. Okay, so I'm ready to calibrate the 4.7 ohm resistor. Let's go back and hit FRA run. And it looks like it's starting at just over 13 dB. And by the way, FRA run is frequency response analysis. Okay, it's coming up to 100 kilohertz here. And again, it looks very flat. I'll get the, here, let's do the measurement thing. Come over here and get the scale. So we got a 0 on the phase at least. Okay, there's 0 degrees right across there. Turn off that guy. And yeah, so it kind of separates like it did before. But look at the blue is the gain. Look how flat that is. Let's get the cursors on. And they came up where I had it before. 14.8 or 14.02 and 13.1. So about 0.9 dB difference. And again, the phase kind of separated around 100 or 200 hertz. That's the scope probe. So it looks pretty flat. So these resistors look pretty non-inductive. And we'll take 13.1. So 13.1, divide that by 20. And then hit the anti-log, 4.5. So pretty darn close. And then 14.02, 14.02, enter, 20, divide, anti-log, if I can reach that, comes out to 5. So between 4.5 and 5 ohms. So it's pretty flat across frequency band. That's pretty nice. Alright, let's begin the 10 ohm test. I'm hitting start button now. Okay, this is 10 ohms on each one of the outputs of the three-way crossover. Purple again is the current and yellow is the voltage. And the gain you can see came in right around 21 dB. And the phase, that's minus 12, there's 3. So it looks like it's up close to 0. Alright, so it stopped at 100 kilohertz. 20 kilohertz is right there, so we really only care, you know, for the audio frequencies out about there. Okay? And we can see a little bit of a wiggle here in the ohms. The ohms look pretty flat, had a little bit of a bump right around the crossover, the lower frequency crossover. And then it kind of wiggles down, and again at the crossover the higher range. So just right around the middle range it kind of dropped down. So let's see, let's bring the measurements up, bring on the cursors, and cursor 1 we'll put at the peak of this first one, I guess, and that's 21.9 dB at minus 5.9 degrees at 1 kilohertz. Let's get the second cursor over here. We'll go down here at the bottom, I guess. And that one's at, well, it's at 3.4 kilohertz, 16 dB at minus 4. So those are kind of the extremes. But if I take the cursor number 2, well, right there at the bump where it straightened out, that's right around 5 kilohertz. And out here it's about 20.4 dB, and over here at the beginning is about 21.19 dB. So it's pretty flat through here. You can see the delta here between this one. So even between the extremes, the delta is about 5.7 dB and 1 degree. So the phase, you can see it's about 9 degrees through here, drop down to 21, minus 21 degrees, kind of same over here, and then in between it's around minus 6, minus 5 dB, or it's around minus 5 degrees. Here I can get the scale with the 0 to make it a little easier to see. Okay, so there's 0 degrees right there. So you can see there's not a lot of phase shift. Right down in here, it drops down, you know, to minus 20 something degrees, but not a lot. And the gain is pretty flat too. So it's very flat, except right through here, the two crossovers in the middle range here. Alright, so I'm ready to start the scan with 4.7 ohms on each one of the outputs. So let's go ahead and do that. Take a picture of that in your mind right now, and let's go ahead and run it. Now it does auto scale, so we'll move the scales around a little bit, and there's our yellow against voltage, purple against current. And when they're on top of each other like that, you can tell they're pretty much in phase. Alright, so it stopped at 100 kilohertz again. Now this is 10 kilohertz and this is 20, so right there's 20 kilohertz. So that's kind of the audible range, but I just go out to 100K just to see if anything weird happens. Now you can see how things really changed here. It's 14 dB right here. Well, it's near 14. And then it goes up to around 26 or something, drops down to 14 and goes back up again at the crossover point. So let's bring the cursors on, do some measurements. Here, I'll change the scale here, put the phase with the 0 right here in the middle. Okay, there's 0 degrees. Let's get the cursors on. Now there's where I had the cursors before. You can see that they're similar spots again. This has gotten lower frequency here, but we got this higher one here. So here I'll move cursor 1 just a little bit over there, which is 3.4 kilohertz and about 15.19 dB. Then cursor 2, I'll bring it down, and that's 2 kilohertz at 14 dB roughly, minus 2 degrees. Now let's bring it up, and that happens around 7 kilohertz. That's 22 dB, and this is 25, so I'll just take it back down to the minimum. So we got kind of the max and the min right here. So the delta is about 11.5 dB. Now as far as the frequency goes, it looks like it goes up as high as 30 degrees, down as low as, maybe 40 degrees, and then back up to almost 30, probably around 20 something degrees. So the phase kind of moves around, but yeah, the impedance did change a little bit, going to 4.7. It did kind of, create a little more reactance in the filter. Wow, what do you guys think? That's kind of interesting, right? What would happen if we put real speakers on there? I think that's the next thing to do, right? So, now what we saw was some sensitivity at the 4.7 ohm resistor. 10 ohm resistors look a little flatter. It's kind of like if you're a kayaker, if you're out river running, and early spring when the water's real high, it's rushing real big, but it's covering the rocks, right? Later on, water drops, the rocks start coming up. So lower impedance, it seems like it had these inductors and so on might have been playing a little bit more of a part in those crossover impedances. Yeah, kind of interesting. Not real easy to design a real flat three-way crossover, but that didn't look too bad, I don't think. Hey, what do you guys think about that? I think what we got to do is put this circuit in a software program and run it. See how close it came out to this. One of the things I think you want to do when you're doing a filter, you want to look at sensitivity. You want to see, wow, if this part right here, or maybe this part right here, changes in value a little bit, how much does that impact everything else? You don't want your circuit being super sensitive, right? So I wonder if that software will help us find that out. I'm going to have to try it out. What do you guys think? Alright, so yeah, we got some fun stuff to do ahead. Hey, thanks for watching. Hey, by the way, that software, Seraph, I think it was, sorry if I'm not pronouncing that correctly, but he suggested a couple software packages that we could look at this, so, you know, you guys might want to take a look at that too, but maybe I'll put one of those in a video. I'll see which one looks like it might be easier for me to learn. Alright, hey, thanks for watching, guys. So that just reminded me, there's another software simulation package that I'm going to show this circuit in, but the packages that Seraph sent me, I'm curious about those. So yeah, I'll take a look, and then we'll get back to you. I'll do a video on a software simulation package, okay? Alright guys, thanks for watching. I hope you like that. Thumbs up, subscribe, all that good stuff. That helps the channel, and we'll see you next time.